Okay, as this title suggests, this is going to be a very brief introduction to antiderivatives. We're just going to focus on what an antiderivative is and the notation with antiderivatives. Just to get you comfortable with all that before we begin the actual process of finding the antiderivative, which I'll go ahead and begin with this challenge. If you know f prime is this function, do you think you can figure out what f is? Take a second to see if you can figure this out. Okay, you should have probably been able to guess and check maybe with your knowledge of derivatives and figure out that x cubed is our answer, because if we find the derivative of x cubed, we get 3x squared. Okay, and so x cubed is our antiderivative. And this process of going backwards is called antidifferentiation. Okay, you will hear antidifferentiation and integration. They're exactly the same. They're interchangeable, so please be comfortable with both terms. The result of this process is the antiderivative, and so we find out that differentiation and integration are inverse processes, just like addition, subtraction, exponents, and logs, and everything else. So being able to move forwards and backwards now. All right, so that's all we'll be doing in this final unit is going backwards from what we've learned from derivatives. Anyway, some notation. So previously we would define a function with y equals something, and then that we would denote the derivative as dy dx sometimes. Sometimes we use y prime, and then f and f prime. Okay, and then we have one more new notation, this capital F of x. And but before I get to that, let's talk a little bit. Now what I'll be doing is I'll be giving you dy dx equals some function. I'm going to be asking you to integrate, and so the answer will be y equals something. Or if I give you this and I say integrate, then you'll be giving me f of x is equal to something. And now what I'm going to be doing is I'm going to be giving you a function, and instead of calling it f prime, I'm just going to call it f, because there are times when we know a function that is the rate of change function. Just because of the peculiar circumstances of whatever it is that we're studying, we know how it changes, but we don't know what the actual original function was. And so what we do is we call that function f of x. Well, if we call that f of x and we integrate, then what would we call the antiderivative? And so we had to create this new notation, the capital F of x. So this is the antiderivative of f of x. And so more formally, here's the definition of the antiderivative. Okay. Now you might have noticed a problem in our previous example. Maybe you didn't, but I'll go ahead and point something out. Let's say I have an antiderivative f. And I say find the derivative, and you get f of x is 3x squared, right? Because that disappears. And then I also have this antiderivative. Well, it gives me the same results after I find the derivative. So the derivative of both of these functions give you the same function, 3x squared. So if I start with 3x squared and I ask you to go backwards and find the antiderivative, we have a problem, because we don't get what we originally started off with. So we have to be a little bit more formal with what we're doing. So what we're going to say is, when we find the antiderivative by integrating, what we do is we use the same process that we just talked about. We say that it's 3x squared, but then we're going to add, x cubed, but we're going to add a capital C for a constant. See, C stands for constant. So we know that there could be some sort of number added to this x cubed that we lost when we found the derivative. Maybe that C is 0, and so it was never there to begin with. But maybe it was 5, maybe it negative 5, maybe it was positive 12. So actually we have to add this plus C. And this is going to be something that you're going to have to remember quite frequently. Students will forget to add plus C when they find the antiderivative. They're so proud of themselves for finding x cubed, but then they forget that there's a whole family of functions here. So don't forget the plus c. All right, so let's formalize this a little bit more. This is from a different textbook, but it explains this very well. And so it's just saying both capital F and capital G are antiderivatives of this function f. So we will find the antiderivative of f of x, but the whole family of possibilities will be that antiderivative plus c. So this g of x, g is, they pick g because that's the general antiderivative. It's going to be this whole family of functions, x cubed plus c, or in this case, and x squared plus c. All right, and you can read this further. It talks about, if you hear a differential equation, what a differential equation, well, that's what these are. These are differential equations. When you are given a prime, f prime, some function, and you have to work backwards to find the antiderivative. That's a differential equation. Now, something you should know right now is a differential equation doesn't always have a solution. So just like in chemistry, if we follow a process, a chemical reaction, we can't always undo that chemical reaction. So in mathematics, we can have a function and we want to find the antiderivative. That's not always possible. But for our experience and for what we do, we will always be able to find an antiderivative. All right, so now let's talk a little bit about the notation here, because I'm sure you've seen this long S symbol lurking around, and so we're going to go ahead and define it, because this is the symbol that we're going to use to indicate that we have to find the antiderivative. All right, so let's go back to the beginning though. So if I have a function, and that's my change of rate function, and I want to work backwards, what I need to do is I need to remember that this function is the change of y with respect of x. Right, so if it's a rate function, I have y that's changing when x changes. So what we're going to do is we're going to move this dx over to the other side. And the reason for that is, now what we want to say is, look, we have this function that's changing with respect of x, and we want to find what the original function is. So this is some technical aspect of what we're doing, and a lot of this exists because although we can find antiderivatives fairly easily, sometimes fairly easily, there's a lot of cleaning up that had to be done with calculus, and this is one of the things that they had to do. So, so all in all, what we're trying to say is, if I have this function and I want to do antidifferentiation, that this is the operator, this is the clue that I need to antidifferentiate this function. And all this dx over here is telling us is that this function is with respect to x. This is the thing that our independent variable that we're controlling. All right, so this is the notation. This is the integral of f of x with respect to x. And then the result of that will be our antiderivative. And don't forget c, the constant of integration. All right. Now your textbook says it a little bit more cleanly and gives you a concrete example. So if we want to find the integral, the antiderivative of x squared with respect of x, then we get the antiderivative 1/3 x cubed plus c. All right. So this is the integral of x squared with respect to x. That's how you say this part here. All right. And so once again, capital F is the antiderivative. If I find the derivative of the antiderivative, I get my function. Okay, and one last note, that this is all called indefinite integration. Indefinite integration. You'll understand why a little bit later when we talk about areas and when we talk about definite integrals. All right, so hopefully you're comfortable with all of that.